In this video, I'm going to go over how we write out balanced equations from text. So this is like as opposed to if I give you a balanced equation already written in formulas. It's easy, you just balance the numbers out. But this is when I kind of tell you a sentence and you have to actually write the formulas first and then write the coefficients. So let's go through some basic tips for this. These aren't necessarily like the rules. It's pretty self-explanatory. You just write down what's given to you and then you balance it. But there are some tips that you'll probably need. First, the most important tip, you got to know your naming rules. I mean, I've made a couple videos. There's hundreds of videos on the internet, tons of worksheets you've gotten. You have to know your naming. And the problem, if I start out by saying aluminum chloride reacts with something and you just write aluminum chloride like that, you're going to be in trouble. I mean, this is not aluminum chloride. If I say aluminum chloride, you're going to have to say, okay, aluminum is 3 plus, chloride is minus, so we crisscross the numbers, it's going to be AlCl3. And if you try to balance it with the AlCl, you might find it's literally impossible to balance. Okay, so you have to know your naming. Okay, make sure you're 100% confident on your naming. Next tip, metals act as lone atoms. So when it comes to a metal reacting in some kind of chemical reaction, they act as lone atoms. So if I tell you something like, zinc reacts with oxygen gas in the air, you just write the zinc as Zn. You don't do Zn2, you don't do Zn2 plus unless I tell you it's a zinc ion. You just write Zn. Or if I tell you iron, you just write Fe. Or if I tell you, if I tell you any kind of metal, it's just a lone element. So metals act as lone elements. Rule number 3, Brinkelhoff. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. These elements are diatomic when by themselves, meaning if you just have a sample of one of those elements, it's always going to pair up. So if I tell you right now, we're breathing in oxygen gas. Oxygen gas is O2 gas. Or nitrogen gas is N2 gas. Or, if I have a sample of bromine, which is actually a liquid at room temperature, if I just have a beaker that says bromine on it, well, that's not going to be Br. It's going to be Br2. That's when they're by themselves. Now, don't think they're always going to be paired now. For example, if you have sodium chloride, you guys all knew this coming into chemistry, that's still NaCl. It's not going to be all of a sudden NaCl2 because it's a Brinkelhoff. No. Only when the chlorine is by itself as a sample of just chlorine, which in this case would be a gas, then it would be Cl2 gas. But sodium chloride is still NaCl. Aluminum chloride is still AlCl3, only when they're by themselves. Okay. Next tip, the phrase burns in air or combust means plus O2 gas. So if I say iron burns in air or iron, well, you wouldn't say iron combusts, but combustion is a special type of reaction. It's when an organic compound, something containing carbon, combusts is when it basically turns into carbon dioxide and water. But anytime you see combust or burns in air, you're going to add oxygen gas. Because, in order for something to burn, you need oxygen. Step 5, when strongly heated does not mean plus O2 gas. This is not the same as burns in air. A lot of chemical reactions, generally like decomposition reactions, will happen when something gets hot enough, but it's not going to react with oxygen gas. So watch out for the wording. When strongly heated does not mean reacts with oxygen. Words like produces, yields, forms, or creates, or decomposes, turns into, those indicate you're going to make the arrow, meaning you're going from the reactant side on the left to the product side on the right. Step 7 includes state symbols when they're stated or when it's obvious. Okay? By stated, I mean if I tell you of aqueous sodium chloride, you're going to write NaCl aqueous. So let's just make sure we're clear on what the state symbols are. There's 4 of them. If something is a solid, like if we have NaCl solid, that's going to look like this. This is what the salt in your salt shaker at home looks like. NaCl solid. And it's generally written as a subscript, meaning it's like small and to the right. If you have NaCl liquid, if you actually manage to melt that salt, which you could do at like 800 degrees Celsius, we write L here. But if you just write a lowercase l, it's going to look like a 1. So we do a cursive L, like a little loop, NaCl liquid. If you manage to boil that salt, well, now we have gaseous salt, NaCl gas, would look like this. And the last state is aqueous. Aqueous means it's dissolved in water. Now, a lot of times when we do reactions, we're going to deal with aqueous compounds, and that's very important. So NaCl aqueous. Okay? Big difference between these two. Liquid means the salt itself is actually liquid, meaning you melted the salt. This would require extremely high temperatures. Aqueous NaCl means you took solid and dissolved it in water. So this is like salt water. When the states are given to you, when they're given, or when it's obvious, and by obvious I mean something like this. If I tell you something reacts with oxygen gas, well, if I say oxygen gas, it's going to be stated. But you should know that oxygen in its natural state is a gas. Hydrogen is going to be a gas. Nitrogen is going to be a gas. Generally, anytime I mention a metal, it's going to be a solid. We can assume it's room temperature. If I tell you a sample of iron reacts, we can assume that's going to be solid. Now, there are some exceptions. You probably know mercury is a liquid at room temperature. Gallium is also a liquid at room temperature. It's kind of up to your teacher how strict you want to get on this. But what I say is when it's obvious, if you have a piece of steel, that's going to be solid. Step 8. When you're done writing it out, go back and balance. If you find it impossible to balance, you probably made a mistake. Again, I mentioned at the start of the video, if you write AlCl for aluminum chloride, well, this might literally be impossible to balance. Now, if you finish out the equation and try to balance, it might be mathematically impossible to balance. If you find that's the case, you probably made a mistake, and you would have to go back and realize it's AlCl3, and now you can balance. All right, so let's go through some examples. Potassium is added to a solution of magnesium acetate, forming solid magnesium and aqueous potassium acetate. One thing I forgot to mention, when it comes to state symbols, the word solution means you have an aqueous compound. Solution means aqueous. Aqueous. Okay, so here we have potassium. Now remember, potassium is a metal, and metals just act as lone elements, so I'm just going to write potassium. Now since potassium is a metal, it's not mercury or anything, we're going to assume that's solid. If I say you're adding potassium, I didn't tell you that you're doing this, in a 1500 degrees Celsius atmosphere. So we're going to assume it's solid potassium is added to a solution of magnesium acetate. So magnesium acetate, I'm not just going to blindly write Mg and then acetate is C2H3O2. I'm not just going to blindly write magnesium acetate. We have to remember our naming rules. Magnesium is 2+, acetate is minus, so it's crisscross. You're going to need 2 acetates to cancel out the 1 magnesium. So we're going to add Mg, one of those, and then parentheses C2H3O2, O2, O2, 2. So this is my magnesium, that's my acetate, and I have 2 of them. And because I told you it's a solution, you're going to write the aqueous there. All right, yields or forming solid magnesium, so that's going to be Mg solid. Again, metals act as lone elements. And aqueous potassium acetate. So potassium is K+, acetate is C2H3O2 minus. So we just write KC2H3O2, and that's aqueous. So we can squeeze that in here. Okay. So that's the equation. Now we have to go back and balance it. So let's see. I notice I have 2 acetates here. So I'm going to need 2 acetates there, 2 acetates. That gives me 2 potassiums, 2 potassiums, 1 magnesium, 1 magnesium. We're balanced. 2, 1, 1, 2. The octane in your gas tank combusts, forming carbon dioxide and water gases. Okay, so this I tell you is C8H18. Now, I didn't tell you the state here, and you could imply that it's a liquid. I believe octane would be a liquid at this, assuming it's standard atmospheric pressure, but this one's not so obvious, so I'm just going to leave it as C8H18. It's kind of up to your teacher how strict you're going to be on state symbols here. But when I tell you it combusts, that means plus O2 gas. Okay, and that's going to form carbon dioxide and water gases. So gaseous carbon dioxide and gaseous water. Okay? So now we go back and balance it. By the way, if you forgot to write the plus O2, you would find it impossible to balance because where did these O's come from if not from the O2 here? So we balance this. Now, when it comes to combustion reactions like you see here, my advice is always H, then C, then O. Look for evens and odds, and when in doubt, double everything. I'll go over what I mean by that. So first let's start with H's. 18 H's, 2 H's. So what do I need here? Well, I need a 9. 9 would balance it out. But before we even write the 9, let me think. A 9 here would give me 9 O's, which is an odd number of O's. But notice, because my only oxygen on this side is O2, it always needs to be even. It's impossible for me to get an odd number of O's on that side, so a 9 is not going to work here. So when in doubt, double everything. You know, I'm not just going to say, well, let me add 10, because then that throw over. I'm going to say double everything. So instead of 1 and 9, let's double it, 2 and 18. Okay, this will still balance on my H's, and now I have an even number of O's, so we should be okay. Okay, H's are done, then C. So here I have 2 times 8 is 16, 16, and notice I'm still okay with an odd number of O's, an even number of O's, and now I just balance out my oxygens. So 16 times 2 is 32, plus another 18, 18 times 1, so 32 and 18 is 50. So I need 50 O's, I have O2, so 25. 2, 25, 16, 18. Number 3 is solution. Solution means aqueous. Of manganese 2 nitrate is added to a solution of ammonium carbonate, yielding solid manganese 2 carbonate and aqueous ammonium nitrate. So this just requires us to know our naming.
Mike Walsh, please call extension 6201. Mike Walsh.
Manganese 2 nitrate.
6201.
What does this 2 mean? That means the charge on the manganese is 2. It does not mean Mn2. Biggest mistake we see. It means that this manganese is a Mn2+, and that's going to react with nitrate, which is NO3-. So we crisscross the numbers, and we write Mn parentheses NO3 close parentheses 2. And because it's a solution, we're going to make it aqueous. Reacts with ammonium carbonate. Ammonium is NH4+. Carbonate is CO3 2-. So we're going to need, we have 1 plus and 2 minus. We need 2 of these. Crisscross the numbers. It's going to be parentheses NH4 close parentheses 2 CO3. And since that's a solution, we write aqueous. Okay? Yielding solid manganese 2 carbonate. Now manganese is still 2, so it's 2 plus, and carbonate's 2 minus. So we're going to simplify that down. It's going to be MnCO3. 2 plus, 2 minus, and that's solid. And aqueous ammonium nitrate. Ammonium is NH4 plus, nitrate is NO3 minus, so it's a 1-to-1 ratio. NH4, NO3, and that is aqueous, so we squeeze that in over here. Okay, and now we just balance out. So let's see, doesn't really matter where you start, but I notice I have 2 ammoniums here and 1 here, so I'm going to put a 2 there. That gives me 2 nitrates, 1 manganese, 1 manganese, 1 carbonate, 1 carbonate. 1, 1, 1, 2. In the Haber process, famous chemical equation, hydrogen gas and nitrogen gas react, forming ammonia gas. Not ammonium, ammonia, which is also called nitrogen trihydride. So, hydrogen gas. That's going to be H2. Why is it H2? Because H is a Brinkelhoff. Okay? Whenever hydrogen's by itself, it takes the form of H2. That's going to react with nitrogen gas. That's also going to be a diatomic. Brinkelhoff. There's that N in there. H and the N are both Brinkelhoffs, both diatomics. And these are going to form nitrogen trihydride. This is covalent naming, so it's 1N and tri is 3, hydride is H. So it's going to be NH3, and that's gas. Okay, now to balance this out, I'm noticing 3 hydrogens and 2 hydrogens. When I see 3 and 2, I got to get them both to 6. So I'm going to need a 2 there and a 3 there. And now I have 2 nitrogens and 2 nitrogens were balanced.
Watson, please call extension 6292. Mrs. Watson,
Okay.
extension 6292.
This is actually a famous equation because this is kind of the first time when this was done artificially that humans were able to fix nitrogen. What that means is pull nitrogen out of the air and turn it into some kind of meaningful compound. And why is this important? Because this is fertilizer. This process allowed us to feed the entire world, and the population boom you saw happening from 1900 on was due largely to this process being kind of mastered. The unfortunate downside is that NH3 is also used in explosives. So while this saved countless hundreds of millions through food programs, it also cost arguably hundreds of millions of lives due to the explosives of warfare. Very interesting process. All right, step 5, bromine. Bromine reacts with sodium iodide to form sodium bromide and iodine. So bromine is a Brinkelhoff. You can't just write Br, we're going to write Br2. Now I didn't tell you the state of matter here. Bromine is actually a liquid. Your teacher might expect you to know that because I know in my classroom the periodic table is kind of color-coded with different states, but that's up to your teacher. I'm just going to leave it as bromine. Reacts with sodium iodide, which is going to be NaI, sodium iodide. This one I write it like this because I know that it's 1 plus and 1 minus. To form sodium bromide, so NaBr. Again, I just know from doing these enough. Sodium is +1, bromine is -1. Nice easy 1-to-1 ratio. And iodine. Okay, Brinkelhoff. The I in Brinkelhoff is iodine. So when iodine gets bumped out, it's going to become I2. Again, in terms of state symbols, go with what your teacher says. In this case, even though I can assume sodium iodide as an ionic compound is going to be solid, I'm not necessarily going to write this one in because it's not given to me here. So, in terms of balancing, I see 1s and 2s. That is pretty obvious what we're going to have to do here. 2 bromines, 2 bromines, 2 sodiums, 2 sodiums, 2 iodines, 2 iodines were balanced. Steel wool. Assume 100% iron. Burns in air to form iron 3 oxide. Steel wool is like Brillo pad. We've worked with these in the beginning of the year. Steel is technically a mixture. It's about 99% iron with about 1% carbon mixed in. That carbon gives it certain properties that are very beneficial. But we're going to assume it's 100% iron. So if we have a sample of iron, it's just going to be Fe. And I can assume that that's definitely going to be a solid. So solid iron burns in air plus O2 gas to form iron 3 oxide. We have to know our naming. Iron 3 means we have Fe with a 3 plus. Oxide is oxygen 2 minus. Crisscross, Fe2O3. Okay. To balance out, let's see. I'll start with my O's here. So I have O2 and O3. 2s and 3s, I need to think 6. So 2 and 3, that'll balance my O's. Now that gives me 4 Fe's, 4 Fe's. 7, zinc reacts with copper 2 nitrate to form zinc nitrate and copper. So, well, zinc is a metal. I'm just going to write Zn, and I'm going to assume that's solid since it's a metal at room temperature, solid at room temperature. Copper 2 nitrate. The 2 means it's a 2 plus. So I have Cu with a 2 plus charge, and nitrate is NO3 minus. We crisscross. We get Cu NO3 2 to form zinc nitrate. Zinc nitrate. Now you might say, well, why don't we need a number here like a zinc 2? Well, that's because zinc is always 2 plus. It's part of that 3-to-1 rule. So zinc is 2 plus, nitrate is minus, so it's Zn NO3 2 and copper. And for the copper, we can assume that's solid because it's a metal. And this, you can see, is actually already balanced. Finally, in the process called lime burning, solid calcium carbonate is strongly heated, forming solid calcium oxide called lime and carbon dioxide. So solid calcium carbonate, calcium is Ca2+, carbonate is CO3 2 minus. 2 plus, 2 minus, it balances out to CaCO3, and that's solid. Is strongly heated, not the same thing as burns in air. So strongly heated just means forming this. So this is what we're going to write. Some textbooks will tell you to put like a little triangle up there to show that heat's being added, or some will tell you to write the word heat up here. That's kind of up to your teacher. I'm just going to write it as the arrow. It's going to form solid calcium oxide, CaO, solid. Again, I'm not just doing this blindly. I know that calcium is 2 plus, oxygen is 2 minus, so it's going to be CaO. And carbon dioxide, CO2. Now this, I'm going to assume carbon dioxide is going to be a gas here. Again, the assumptions about the states, that's really up to your teacher. And in terms of balancing, looks like it's already balanced. Okay, so that's how we're going to write out our equations. Those are the 8 examples I have. And just as kind of a looking ahead, the next step is you're going to actually, I'll tell you the first half, and then you're going to have to complete it. Like it's called predicting products. Now something like this, it's not really going to fit an exact formula, so I wouldn't give you this. But something like this I could give you. I could just say zinc reacts with copper 2 nitrate. That's all I could tell you. And then you have to figure out what it's going to form based on the types of reactions. Same thing with like this. I can tell you octane combusts. That's it. And you finish it out from there. So that's what's coming up next.